the language of the universe.
But I don't understand it.
Everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 95, where today we have Dr. Achanta Venu Gopal here with us, the director of the National Physical Laboratory of India and a fellow researcher at the TIFR. So, Dr. Achanta, maybe you want to say a few words of hello to our audience. Introduce yourself.
Good morning. It's evening here in India, but it's good morning, Sunday morning. So thanks for tuning in on a Sunday morning. Right, I'm looking forward to this. This is exciting because this is my first time and interacting, though it's a faceless interaction. Hopefully, I'll be able to generate some interest in what I work on and what we do at NPL as well as at TIFR.
Awesome.
So look forward to this podcast.
Great. So we're going to dive into all of the interesting physics topics that you are involved in. But before we actually get into the podcast, we have a quick little news introduction. So in terms of the NFT giveaway, we are announcing the winner for last week's and also the next one coming up. So we are giving away today the third NFT in the collection. And we did like a random number generator, and we'll contact the winner on Instagram, but the winner is Goncalo Martins Rice on Instagram. So
That's their Instagram handle.
We'll contact you, and we'll let you know that you won the third NFT. And so if you head over to our Instagram right now, we will have the fourth one being given away. So yeah, we'll have all the rules on our Instagram on how to get in on that.
Yeah, the NFT, as we said, right now it means just for fun. But a little bit later on in the podcast, I think we can actually make a use for these actual tokens. So let's see where it goes. Continuing on a little bit, just a quick little news segment before we get in. Followers are sitting at a calm and easy 21,500. Our downloads are, again, nearing even closer. I mean, closer every episode, right? Even closer to the nice 400,000. We're at 380 right now. While our followers or subscribers on YouTube are 2,250. I think we actually got more this week than we did last week. So that's always nice. So thank you to everyone who continues to follow, continues to subscribe. Keep doing that. If you're on YouTube, smash that like button for the algorithm. And if you're on Spotify, just rate it.
Rate it 5 stars.
Why not?
And finally, for the comment of the week on YouTube, this week's comment comes from the Idea Space. Actually, Clément, who we interviewed last week, he left a comment. He says, "Awesome interview. Shout out to Parker and Ray for absolutely killing it." So if you want to be next week's comment of the week, make sure to go over to our YouTube channel, subscribe, and leave a comment on this week's episode.
Yep. I mean, that's basically it. I don't think we have anything else. Okay, so I think we can safely get a little bit into the podcast. So we can start with the classic question that we happen to ask every single guest on this podcast. So Dr. Achanta, let me ask you, how did you get into the field of physics?
Right. Teachers, obviously. Right?
Yeah.
The teachers got good teachers who could motivate me and put me to, channel me towards physics when I could have gone in other ways. Mm-hmm. So other interests which I was probing was business administration, but then my teachers, they encouraged me that why don't you do 2 more years? There is nothing for you to lose. If you want to shift, you can always go in another direction. So, and yeah, never looking back.
Is there any topic that you remember that, you were studying in physics and it just made you go wow, I really want to pursue this? Optics.
It's always optics.
Mm-hmm.
So the experiments with light, interferometers, using lasers for the first time, right? It's always optics which intrigued me.
So was it just like the naturality of it, like, oh, it's everywhere, so nice to have it deduced, or what was it about optics? Was there anything in specific, or was it just like the field itself that just intrigued you in general?
If you just think about it, it looks so simple, right? Like, so light travels in straight line, right? Like, doesn't interact with another beam which is going unless you make special conditions.
Mm-hmm.
But then there's so much interesting you can do, right? Not just with light itself, but how light interacts with matter. Right. So
Hmm.
and when you go to lower dimensions, like so for example, you cannot measure how two electrons interact with each other, how electrons interact with, say, for example, the lattice vibrations, which are the phonons. Right. These time scales are beyond the or limits of the present day electronics, but then you can use optical spectroscopies, right, to probe these at say sub-picosecond to few femtosecond level time scales, right? So light offers like so much to study, not just how properties of light itself, but how light interacts with matter and what we can achieve with it.
Right. I also find optics so interesting as well because if you think about not that long ago where we didn't have all this like modern technology, it's something that was really mysterious and hard to actually study. And I always like to think about the times where um, scientists back in the day would try to make assumptions about light. And, you know, at the time they couldn't really prove themselves right or wrong. They just had to kind of take a guess and then try to go from there.
Yeah, optics was very different, I guess, right? In the older ages. Even I mean before someone like Einstein and with special relativity and all, I'm assuming the world of optics or anything really would be quite different. So so here we are. You have stayed on these extra 2 years, and you've now got into or kind of like physics a little bit more. So was this like in your undergrad that you stayed on, and then you just continued on to like a PhD after, or how did that process work back then?
Right. So I went on to do my master's in Central University, Hyderabad, which was kind of mecca for optics at the time with really good teachers who are in the top in the world in quantum optics, for example. Right. So, for example, Professor Girish Agarwal and right. So they're good names, good motivating teachers. Like so, I went on to do my master's at University of Hyderabad, also called Central University of Hyderabad. Right. And then I moved to TAFR to work on spectroscopy, optical spectroscopy, especially these ultrafast dynamics, like so how carriers interact in semiconductors.
Ah, that's very
And
cool. Yeah, sorry, continue.
mm, so yeah, that was the journey, right? Yes.
That was a journey. So again, we see itself that optics has clearly evolved so much in like the last, again, since special relativity. I'm just going to keep that as like a pivot point. Since then, I'm assuming like it has evolved quite a lot. And you've now researched at the TIFR, which to our listeners, the Tata Institute for Fundamental Research in Mumbai, India. And now you are also at the National Physical Laboratory in New Delhi. And you've also, I'm assuming, been working at these both spots for some amount of time, considerable amount of time, taking that you went to TIFR right after you graduated. So I guess my question is, if optics changed so much from special relativity, how much did it change since when you've been in it? How have you advanced with the technology, or how has the technology advanced with you?
Right. So now we more look at, I mean, the classical optics is still interesting, right? So what we're talking about the old times, like, so the lens maker equations that, I mean, these are all fundamentals which we need to, if we want to develop a good instrument, optical instrument, of course, I need to have strong basics in my classical optics. Right. If I want to look at applications of optics, where the photonics area has evolved, right? So it's completely application of these. The basics has come out considerably well, like the fiber optics and right? We're also talking about single photon communication and all these things, right? So it has evolved quite a bit, moving from say millions, sending millions of photons over fiber or free space communication to we're talking about sending single photons, detecting single photons, or generating single photons, right? How to generate them and how they interact with matter, right? So it's considerable progress which has happened over the last I don't know 70, 80 years at least, because it's also linked to semiconductor development. And now we're trying to look at, people talk about if we can replace electrons with photons.
Hmm.
Right?
Right.
So, but we're still off, but we're inching closer.
Is
Right?
that the art of photonics? Is that the whole research of photonics? Like, can we make photons, electrons?
Yeah, I mean
Oh,
that's can we replace, for example, electronic circuits with photonic circuits, right? So the photons already replace electrons as far as communication is concerned, right? Can we go to computing as well, right? When we talk about information processing, we have communication and computing, both are there. In communication, the photons are already replaced electrons in almost all the places. Right now, coming to computing, right? Can we replace like that? That's a long way off, because having photonic integrated chips, cost effective as well as high computing performing chips is something which is still a challenge.
wow. I mean, millions of photons in a fiber to one itself. I think, I believe a couple decades ago, sending one photon or measuring one photon was considered impossible, was it not?
Right. Yeah. The detectors again, if you look at them, like so, the detectors are known in semiconductors. For example, the good old avalanche photodiode, right? We know the avalanche process, avalanche breakdown process in semiconductors, right? So you just use the same technology to detect single photons. For
Sorry, could
example,
you
you
maybe
bias
maybe
your,
briefly
yeah,
explain
I'm
that
just
process? Yeah, because I have no
yeah, I'm
idea.
just trying to do
Yeah,
it.
go for
Right?
that.
So if you have a p-n junction, right, of semiconductor, a p-doped and an n-doped, and you form a junction, and if you use in a forward bias where p is connected to the positive of the battery and the n is to the negative, you have the forward bias and you have the diode characteristics, right? So, but you can also do the reverse bias where you change the polarities, right? In that, if you keep on increasing your bias voltage, at some point, like you see what is known as the breakdown, right? So it's like you have so many the kinetic energy of the electrons which are there, like so you're pushing them so fast that like they go and knock off other electrons which are around, right? So that causes an avalanche, right? So it's the same process which is used for single photon detection. So for
Mm-hmm.
example, your bias is just before the breakdown voltage where this avalanche process starts, and then a photon falling on your diode, right, which is reverse biased, so that triggers the avalanche, right? So you can get a, when one single photon is absorbed, like so you get a output pulse, right, which you can shape and detect.
Hmm. So how do you know if it's exactly one photon that you're detecting and not just like two photons hitting it at a very similar time?
Right. So the good old Hanbury-Brown-Twiss experiment, which is known in astronomy as well. Like the idea is that like if you put a 50-50 beam splitter, so 50% of the light is getting reflected and 50% is getting transmitted. If you have a single photon, right? So if you have many photons, so half will go into one detector, which is in the um, reflection path, and the other half will be detected in the transmission path by the detectors. But if you have a single photon, it'll either go into the reflection or into the transmission, but not to the both the detectors. So what we do is the standard technique is to measure the so-called second order correlation function, right? Which is finding the probability of finding the photon in both the detectors at any given time, right? So when the path lengths of the reflected and the transmitted are equal, right? So that's a t equal to 0, right? So the photon can only go either in the reflection or in the transmission.
Mm-hmm.
But if you have a time which is not equal to zero, which means there can be a stray photon coming from behind or after the photon which we want to measure. So that can trigger both the detectors, both the reflection and the transmission detectors. So you'll have a non-zero probability of finding a detector in both the detectors at t not equal to zero. But at t equal to zero, you'll have only one single uh, detector triggering. So the probability of finding photon in both the detectors will go to zero.
Okay.
Okay, that's making sense. But continuing on with with these photons itself, I'm just trying to relate the art of photonics that, again, I know nothing of, to detecting these photons. So what I guess my question can be is, where does the detection of the photon, or what does the detection of the photon tell you about the interaction with these particles? Because I'm assuming what you're doing, again, completely correct me if I'm completely wrong, but I'm assuming you're like sending out a stream or maybe a singular photon interacting with some electronics, and then it's being detected. So I guess my question is, what is that detection telling you? Or did I just get that completely wrong? Is that not what you're doing? What is that photon really doing in the first place?
The technique which I said is for saying whether we have one photon or more than one photon, right? But this photon can be used eventually for, say, for example, for quantum, like single photon level interactions, right? So when we want to compete with electronics, like when we say like photonics may one day replace electronics, like it's a far-fetched statement, but at the present, because the cost of chips, electronic chips is much cheaper compared to, because we are packing more number of transistors into the chip, right? And also the power consumption is much lower. So now we want to have processes which will work at few photon level, right? So that's one application where like we want to use low power consuming photonic uh, circuits, right? So that's one area like where these photons can be used. And of course, like for communication point of view, a single photon is always better than many photons, because if somebody steals that single photon, we know when I'm sending information to you, if somebody steals the photon which I have sent you, automatically we'll know that like, okay, somebody is stealing the data. Okay. So the security increases if we use the single photon communication.
And so, are the complications in developing photonics, do those arise when considering the quantum effects that come into play?
You're asking about how complex it is.
Yeah, like the difficulty in developing photonics is in considering the quantum effects that kind of play with the system.
Right. The whole game of this argument about can we have an alternative for electronics is because we're packing more and more transistors, and eventually when we go to single atom level, or so we're talking about quantum effects, right, where these devices will be interacting with each other, right? In terms of photonics, pure photonics, the problem is if you talk about a photonic device, right? Uh, why can't we see an atom with in a microscope, in an optical microscope? It's because it's below the diffraction limit, right? Like, so we see something when we get the reflected light, right? Or at the limit of the resolution, it's the distortion in the wavefront or distortion in the optical beam, which will tell us like, okay, there is something, some obstacle, some particle in the path of the optical beam, right? So the diffraction limit says that the particle size should be greater than or equal to lambda by 2. So if you're talking about blue light, like so 400 nanometers, so the particle sizes should be at least 200 nanometer or so. The sizes are much bigger, right? Compared to electronics, where we're talking about 7 nanometers is the smallest feature which you have in the electronic circuits is in the chips. So here we are talking about fundamental limitations coming from the diffraction limit, right, which puts it at lambda by 2. These are much bigger compared to the electronic circuits which are possible. So how do we overcome this? So one area people are looking at is these metamaterials, right? So you can have initially people are thinking about using what are known as the plasmons, which are surface waves. So if when you have a metal, you have large number of free electrons on the surface, right? Under certain conditions, you can excite a charge density wave. So you have more number of electrons at one place and less number of electrons at the other place. And this charge density wave propagates along the interface of a metal and a insulator, right? So the metal dielectric interface. So because this charge density wave, the plasmon mode is a surface mode, which means that close to the surface, within say 10 nanometer of the surface, you have this confinement of the field going on. So from optical domain, where you are talking about lambda by 2 features, now you are confining that electromagnetic field to the surfaces of the order of like tens of nanometers. Okay. So you are bringing down the field to much smaller dimensions, which are comparable to the electronics. Right? So these are challenges. So now how do I manipulate the photons? So we talk about these so-called metamaterials, which are designed materials with sub-wavelength featured structures, or like atoms forming a lattice. So here the entire material is made of some unit cells which are much smaller than the wavelength. These are sub-wavelength featured, so that one wavelength of light will not see the material as, or one layer as a one layer, right? Because it's not feeling the one wavelength which you see, right? It is not seeing the each layer separately. It just sees the overall structure as a unit, right? So you'll have what is known as an effective medium, right? As far as the light is concerned, the refractive index is not concerning to any one particular material, but it's a new material which you are designing. So going towards metamaterials, right? So this is, you can design as per your wish, right? So you want some particular functionality, you can design this metamaterial for that particular functionality.
So yeah.
Going towards like, yes, I mean, these are the paths people are taking, so that like you beat the diffraction limit, and also have, say for example, I want to put a single nanoparticle inside them, right? A single nanoparticle is like an atom, right? Compared to an atom which is in vacuum, right? It doesn't interact with any other surroundings. So you have very precise energy levels for these atoms. Right? Now you have a nanoparticle. So the nanoparticle is a solid state equivalent of an atom. Right? You also have, because of the small nature, where the size of the particle is comparable to or smaller than the de Broglie wavelength. So the wave function of the electron inside this particle. So the electron energy levels are quantized. So you have discrete energy levels which are forming when you have a nanoparticle. Right? When you put this inside these metamaterials, you can have like an atom inside a cavity kind of structure. Right?
That actually is quite fascinating, because I was thinking about how you were trying to describe or describing metamaterials, and how like the photonics and how our understanding of all our limits basically kind of is the only thing that's really stopping us from really moving forward, right? So all these fundamental limits are really the thing. So I don't know if this might be a really basic question at this point, especially, but I do want to ask, very simply, what's the sheer advantage of photonics? Because it seems like you're doing so much more work now. Obviously, that will pay off, I'm assuming, in the long run. But I guess the question is, apart from like the obvious, okay, it's like 50,000 times faster. I guess the question is, like, what is the actual advantage of photoelectronics? Like, how does that play an advantage in that part?
Right. As I said, one is what if we reach some limits in electronics
Yeah, I guess that's the
from technology
theoretical, for
perspective,
sure.
right? Yes. Then the second question obviously is the speed, right? And bringing two electrons close together and traveling, or or if you have two wires, when you bring them close together, there is interference and all that. That doesn't happen if you have two photons. I mean, two photonic channels, for example. So these are, I mean, advantages.
That makes sense. How are these metamaterials then constructed? Are they constructed in like using, I'm assuming, like using very high precision lasers and whatnot? I'm assuming, like, again, just explain it rather than me trying to guess how
Okay.
exactly.
Uh, I mean, metamaterials, as I said, they do not exist in nature. So you think of um, some functionality which you want. For example, if I want to have I want to improve solar cells, right? So what do I need is I need to absorb as much light as possible in my solar cell, right? So for this, I need to have highly absorbing material, right? I start with that. Right. So for that, I need to confine the field to the active layer as much as possible. So I need to design so that like it acts almost like a cavity where like one of the layers you have strong absorption, right? And so for this, you start off with either metal dielectrics, a combination of metal and insulating layers, or metals are lossy. So now people are looking at using all dielectrics, all insulating layers, so alternating layers. So you design it. And then depending on the structure, so there are different ways. The simplest is making alternating layers of these materials. Right. So there you use deposition techniques like sputtering or very high precision if you need, like, so you can go to molecular beam epitaxy. Right. If you want patterns, so for example, you have a material and then you want to make some patterns, like for example, discs on top, right? So there you use some lithographic techniques. Yes, I mean, as you said, like, so laser machining is one thing, um, but its electron beam lithography is mostly preferred because it has focused ion beam is also used, right? So it depends on the structure, like whether you want holes, whether you want pillars on top of your structure. So that there are, you choose your technique depending on availability as well as ease it gives in making these structures.
So has it been done already? The act of actually confining a single photon and being able to control and direct it.
Right. Yes, I mean, yes and no, because uh, what is the current challenge with single photons now is on demand. Right. So it's like a switch, right? You turn the switch on and then a single photon comes out,
Mm-hmm.
right? So that's on demand single photon generation is still a challenge.
Mm.
It's not done, right? But you have structures where you can confine a single photon in a structure, right? And that has been achieved.
Mm.
So if the on demand is not still completed, what exactly are we completed, or what exactly have we completed when it comes to single photon detections? Is it like how have we
So
deduced
then,
that if the
right. As I say, like, so we have these metamaterial structures in which we have a single nanoparticle inside them. And then because these have discrete energy levels, so when we excite an electron from ground state to the excited state, so the electron recombines with the hole in the valence band and then emits a photon out. Because it's one photon absorbed will excite one electron up. So when re-emits, you get one photon out.
Mm.
That's the ideal scenario, right? So you do get these single photons out, and then we can characterize them. Right. And the simplest way of doing is you take room light. It'll have billions of photons in what we're seeing, right? So you can put filters, right? Just some color insensitive filters, and then you can reduce the intensity to such a level that you can go down to a single photon. Right. So, but then it won't be that a photon is coming all the time. One photon is coming out of these filters all the time. Like, so for example, if you're measuring for say 100 seconds, you'll have one photon, right? So these are as I said, like, so these are not on demand wherever, whenever you want, you're getting it, but then you do have single photons.
So why haven't we been able to do on demand? Because as you just explained it, just exciting this metamaterial doesn't sound hard to me. Like, is there something that I'm not understanding about the metamaterial? Like, why is it hard to excite this electron?
Right. So again, it goes back to the light matter interaction. So how when you're exciting with optics, for example, you're shining a light, so the light is absorbed, so the light wavelength is such that the photon energy is above the band gap, so that an electron from the valence band is excited to the conduction band. Right. But how can we make sure that only one photon, because there are many electrons in the semiconductor system, right? So how do we make sure that only single photon is getting absorbed, and precisely only one photon, and that also is triggering this electron hole recombination to re-emit the photon, right? These are all probabilistic, right? Like, so there is say 20% absorption, there is 30% absorption inside the semiconductor. By making this metamaterial structure, we are making the photonic density of states in such a way that, like, the probability of absorption of a single photon is increasing, or outcoupling of a single photon is increasing, right? But still, it's the total quantum efficiency, as we say, like, so of how this photon is getting absorbed, and what is the probability of that electron which is excited, it's not interacting with the phonons and getting into I mean, losing its energy without recombination, right? That's also possible. There are defects, there are other kinds of processes which will make sure that the electron not necessarily recombine with the hole and emit a photon. Right. Eventually, I guess, like, so we need to combine electronic and photonic ideas, where we have an electrical pulse which will do the trigger, and then excites an electron, and then the electron hole recombination happens, and then the photon is emitted out.
But if we're trying to combine electronics and photonics together, wouldn't the entire like system be limited by the I guess the capacities of the electronics, and so we wouldn't be really reaping the benefits of purely photonic systems?
Right. I mean, that's where is the challenge is, like, so how do we? I mean, for photonics, we need the layers to be very thin, right? So can we have good conduction of electrons? Like, so then would electrons nicely tunnel through or pass through these layers, or propagate within these layers, right? So you have doped semiconductors, for example, for the electronic structures, right? So you have semiconductors which are used, right? Now, if you're the limitation is choosing these thicknesses, choosing the materials suitable for both electronics as well as the photonics. Right? So when we talk about a metamaterial, very precise thicknesses or the dimensions are needed. So would that be suitable for the electronics?
Right.
That would be challenge.
Is there any use currently, or not use, but what, or have you been using, is how I should have said it, this preliminary technology as of yet? Because as you said, we still haven't been able to go through the computational aspect of it, right? Like, it can't, or did I, so you can't so there's one part of the major part of the electronics that unfortunately we're still unable to do. But I guess my question is, have you been able to do the other parts well with photonics, and have been in use pretty well? Or what do you see the differences between that and electronics?
Right. So one interesting part is that you set your target to reach the sky, right, will not be able to jump so high to reach the sky.
Of course not.
But then in the process, like, so we will be learning, we'll be generating know-how, knowledge, right, which will help us do other things, right? So that's the whole point of doing the blue sky research or the basic R&D.
I guess that makes sense. How far are we from uh, a photonic computer, let's say? So a computer run on photonics.
Yeah, I recently read about a week or so ago. I think it's a Canadian company which actually integrated a full photonic integrated chip into the mainframe computers.
Oh wow.
Wow.
Oh wow.
Right.
So
I
it
So
was.
we're
do not
there.
remember the details. Then, yeah, we're inching closer. Yes.
Oh wow. Okay, so that's actually very very cool. So what are so I guess okay, so now that we actually have direct like a literal computer to test this on, have there been, I'm assuming there's definitely been like tests like this versus supercomputers or whatnot. So I guess the question is, well, how much better is it? Because I guess like have you read up any? Because I don't want to ask you if you haven't like read up any more
No,
about.
no,
Okay,
not yet.
okay,
It's not a
it's very new.
fully
It's very new.
photonic thing. So it's just one chip which is used in it,
Okay.
right? So, but for a full optical or the photon based computer to come, an optical computer to come is a long way off.
Long way off. Okay. And the biggest challenge again for that is simply the construction of the materials and the scarcity of it. Is that
Packing,
it?
right? Uh, Packing enough number of components to do the logic operations. And are we going to use the same? I mean, if you want to integrate with the current electronic computers, right? So we need to use a similar kind of architecture. But if it is a fully photonic computer, like, are we going to use the same architecture, same logic operations, or is it going to be different? Right. So there is, I mean, this possibility scope for changing the architecture itself.
So currently we have, I think this is actually a really good question. I just thought of, I think this is actually really interesting to me right now. Currently we have electronics that are working decently well to our standards, right? And we have some crazy supercomputers. Our next goal in the process of processing and computational is quantum computers, right?
Right.
So, I guess my question is, I mean, you are studying photonics, so I guess that's not a very good question to you, but do you think photonics would outweigh quantum computing? And if not, again, this is probably not a very good question for you, but shouldn't we be directing our resources to something that is even better if we're anyways spending the equal amount of time on it? Like if we're trying to figure out quantum computing and we're trying to figure out photonics, but quantum computing is much better, or let's say photonics is much better, then what's the point of doing the other in the first place?
Right. So as I said, just to put in uh, very simplified way, is a quantum computer is a parallel computing machine, right? And the computers which we have, they do serial processing, right? So we do parallel processing by coding using different codes, right? Different coding technologies. We can still do it, right? So it's not the present day computers or the quantum computers. I would see them as different technologies, like which can do uh, completely different ultimate goals, right? Like, so what you can do with a quantum computer is far more challenging and far more challenging than a normal computer which is existing now, right? So to build a quantum computer, yes, I mean, so right now people are using these superconducting qubits because the technology has matured, right? It all began with atoms in cavities, right? So the NMR has been used with very specific molecules having 5, 10, or 12 qubits each resonance is one single qubit operation, right? A qubit So there is also photonic qubits, optical qubits, which are being pursued. Right? So you can have the polarization state of photons uh, as as a um, as a qubit, for example, right? Uh, as a freedom of using it, like so. You have optics based quantum computing architectures also people are working on, but it's not as matured as the superconducting ones, right? So it's not the traditional photonic computer or quantum computer, but yes, when people are also looking at using photons for building a quantum computer. The technology is not matured yet, but yes, I mean, that's one area people are looking at.
So that would be the goal, a photonic quantum computer.
The,
Wow.
right,
Okay.
yes.
Okay.
So I'm interested to know what you actually did for your thesis in writing your PhD.
Okay. So I looked at in semiconductor, right? We have electrons and holes, so valence band, conduction band, right? So I've been using little bit of that in my earlier answers. Okay. So when we have an electron which is excited to the conduction band, right? So it's in certain energy level, right? So now this electron is has to lose its energy and come back to the bandwidth, right? So how does this process happen? Right? So what are the pathways for it to lose its energy and momentum? Right? So the electron interacts with the other electrons. Electron interacts with the holes in the valence band. Electron interacts with phonons, the lattice vibrations. Right. But what happens if we reduce the dimensions instead of having bulk in which you have 3 degrees of freedom, right? Ex, Ey, Ez, the X, Y, Z components of energy as well as the momentum components, Kx, Ky, Kz, right? So they're all, continuously variable, minus infinity to plus infinity. You can always get some scattering component. An electron can interact with another electron with minimal restriction on as far as the energy and momentum conservation takes place, it can scatter with them, right? Interact with it. But when you bring these electrons and holes to dimensions close to the uh, Bohr radius, one wavelength of electron or the particle, right? So then you start seeing this like the potential well problem in quantum mechanics, right? So it's like we are making a potential well by having high band gap and low band gap material, and then so basically a low band gap material is sandwiched between two high band gap materials, right? That forms a semiconductor based potential well, right? It's called a quantum well. So when you have this narrow, say sub 100 nanometer thick semiconductor layer, and the electron is inside that layer, how does interaction of that electron with other electrons, holes, and the lattice, uh, compared to, for example, when the electron is free to move in all 3 dimensions? Right? In a potential well, it can move in 2 dimensions. It's confined in one of the directions, right? Or you can have a nanowire in which the electron can only move in freely in one direction, but in the other 2 directions, it's confined, quantum confined. Or a particle in a box, a quantum dot or a nanoparticle. How these electron are right when you're bringing them to lower dimensions, what happens is the electrons and holes are no longer independent particles, but because these are confined to dimensions which are smaller than the de Broglie wavelength, so the electron and hole are spatially close together, right? So they form a hydrogen atom like particle which is charge neutral, and these are called the excitons. So my thesis was about how these excitons are formed, how these excitons lose their energy and momentum, how they interact with other excitons, how they interact with other electrons and holes and lattice vibrations of phonons. Right? So that was
So what were some like key results that you found in studying this?
Yeah, I mean, it's basically what we showed is there is a dimensional dependence for these things. So we showed by comparing quantum wells or potential wells of different well widths and also with quantum wires, right? So how these exciton dynamics are changed, right? So we measured the lifetimes, we measured the interaction strengths, the scattering strengths, and then showed that yes, as the dimensions are changed, so your scattering strengths vary, right? That's what we showed in our work.
Very interesting. And does this connect in any way to what you're doing now?
So eventually, like, so what I do is use the semiconductors. I still use semiconductors to design these metamaterials. And that's where I mentioned that the holy grail for me is to couple the ideas of electronics and photonics now, right? Metamaterials, and see if we can design metamaterials where we can electrically or magnetically trigger them.
So do excitons interact with photons in a special way?
I mean, they do absorb, so that if the energy is right, like so, and the momentum, so it just energy momentum needs to be conserved, and you can couple light or excite excitons
So just like a
using
hydrogen
light.
atom.
Yes.
Okay. Very
Oh,
interesting.
that is very interesting, actually. So these excitons basically can model. Oh wow, that's actually pretty interesting, because it can be absorbed by all these by all these things. So I was just thinking, because there was a abundant use of semiconductors in all of these experiments, and officially, I don't think we've ever really gone into a conversation about them, because I don't think either of us really know too much about them in the first place to really go into a conversation about them. So, I mean, obviously, we're talking now in specific to you, and we've already kind of discussed how it can, help and what exactly it does in these experiments. So, when you set these conductors up, like, is there a like what's the pro? Because I'm actually very interested in like practical physics, experimental physics. So I'm just like thinking fundamentally, if I were to set something like this up, would I just be taking these conductors and putting them together, physically putting them together with like research technicians? Like, what's the process of you actually conducting one of these experiments, like with these semiconductors? Like, what is the use of these semiconductors in these experiments, and like how do you actually manipulate them?
Right. So what we do in the lab, so we take these structures, semiconductor structures, and we have some fancy lasers which generate, say, 25 femtosecond um, pulses, right? So the pulse width is about 25 femtosecond. So we shine light, the laser light on the sample, and then do spectroscopies, which vary from the simple measure, like so measure the photoluminescence, right? So the light is exciting electron up in the connection band, so that forms a exciton over a short time scale into an exciton by binding with a hole nearby, and then how it interacts with the other excitons, and then depending on that, like it loses its. So initially there is a polarization of the incident light. So all the excitons or all the electrons are aligned with respect to the polarization of the incident light. So the electric field orientation, like so the electron spins are all oriented. Now, over time, like so these electrons are interacting with other electrons, and then they lose their coherence, or they become randomly oriented, right? So this is the coherence time, right? So for any quantum application, right? So you need, for example, um, any measurement which we do is a probabilistic measurement in quantum computing, for example, right? So that means like we're making many measurements and measuring the probability of finding in some particular state of the electron, right? So now, uh, for this to happen, for these many measurements to happen, the coherence time has to be very long. Right. So we look at processes or materials which have long coherence times. How we can look at the coherences and what materials have higher coherence and things like that. So we study different materials and look at their lifetimes.
And these are all naturally occurring materials, right?
Yes, most of them are. Yes.
Okay.
Right.
Okay. So you
So
basically
actually, these are not okay. I should be careful. Like so not all. So most of these semiconductors nowadays, which we work on, the silicon, germanium, these are the group 4 elements are naturally existing. But now the semiconductors are mostly by mixing group 3 and group 5 from the periodic table. Right? We have gallium arsenide, indium gallium arsenide, aluminum gallium arsenide, or you can make aluminum gallium arsenide, antimonide. Right? Or you can mix a group 2 and group 6 elements, right? Like cadmium selenide, cadmium sulfide selenide. Okay. So these are all, these do not exist in nature, but by mixing these compound semiconductors are made.
Hmm.
So that's how we can control the band gaps and get alternating layers.
that's interesting.
I was just wondering, is there any use for superconductors in your field?
As detectors. So now I moved to National Physical Laboratory. So here in TIFR, I was more looking at how to have these single semiconductor nanoparticles, the quantum dots inside these metamaterials and get directional single photon emitters. So that's what I'm working on, and we have some progress on that. Right. So here at NPL, like so, what I'm looking at is the single photon detection. So one is, of course, the avalanche photodiodes. The other one is the superconducting nanowire-based single photon detectors. Right. So that's something which we are looking at, and yes, I mean the superconducting. For me, the superconducting superconductors are useful as detectors for single photon.
So how do those work?
So you have these thin wires of superconducting nanowires, for example, the widths are of the order of like say hundreds of nanometers. Right. So when photon falls, either the photon can get absorbed or the photon can just transfer its heat. Right. So just locally heat the superconductor out of its superconducting state. So it becomes a normal state. Right. So then once that happens, you have voltage developing in that region. Right. The current is normal current which passes through. Right. So that comes out as a voltage pulse which you can detect. Right. So compared to avalanche photodiodes, where these they work only in certain wavelength ranges, so the superconducting nanowires that they work over a very broad band from say near infrared to you can detect like complete spectrum of
Oh, wow.
electromagnetic
So a
radiation.
lot more universal in that sense.
Right. Right.
How do you handle the problem of temperature with these superconductors? Because when a photon or streams of photons and like reaches a temperature differential, it refracts. So I guess my question is, how do you have something, or is it like your whole setup super chilled, or how does that work? Like how are your wires superconductors without the whole setting, the whole setup just being really really cold?
Right. We use a commercial cryostats now. Right. So these are liquid helium based ones. Right. You can go down to right easily to just with pumping. You can go down to 1 to 2 Kelvin temperatures. Right. So these samples are pretty small, so it's easy. Not too much of liquid helium is needed over days. You can run it for tens of liters of liquid helium.
Okay, so it
Right.
doesn't
So
really
because
affect the process or
yeah,
experiment.
the
The whole
bath,
thing is
right,
just changed.
right,
Okay.
right. So
Okay, that makes sense. And in your experience at the NPL, how did that change happen? Because TIFR, again for listeners not from India, is in Mumbai, and NPL is currently in New Delhi, right? So are you still a researcher at TIFR, or did you officially move to the NPL?
Yeah, I'm on deputation, so my lab is working. So TFR is kind enough to let me
Oh, okay.
retain my lab there.
That's
So my
nice.
students and postdocs, they're working in TFR. So the lab is still functional. And in NPL, I'm as got the offer as the director here. Like, so it's a National Metrology Institute. So I'm also learning about the metrology. Right?
That's a little
So
interesting. Yeah. You were talking about your experience in also teaching now. So were you always, was that always a goal for you, or were you just like, oh, I guess now I'm at this national lab, I guess I should start teaching? Or how did that come up?
teaching is always there. Finding time now is a bit challenging, but I will be starting my teaching next week for this semester.
Because
Right.
yeah,
So
sorry.
teaching is always interesting because it doesn't matter how much we know, how much we read, but when we're presenting it to students, like, so there are always questions which pop out, right? And then you try to answer them, and you say it gives a different perspective to the whole of my understanding,
Mm-hmm.
right? So okay, I can also explain this way. Oh, okay, this is
It does.
different outlook, right?
Mm-hmm.
So I see I see over here that there are like nearly 5 to 6, the 7 publications that you have every year that you've been releasing, and now I'm hearing you're also teaching. So I mean, apart from the fact that teaching is probably, as you very well said, definitely takes up a lot of your time, how do you get out 5 publications in a year? Like, isn't one publication like a lot of work? Again, not really knowing anything about publications, if you could care to explain, but what's the process of getting so many out in a year?
Uh, I mean, I should thank my students, right? They're the ones
Yeah,
who do most of
that's
the
nice.
dirty work now, and my collaborators, right? One thing I learned is yes, having good collaborations is important, and once we collaborate for the sake of science, I shouldn't be worried about where my name is in the publication, whether it's a beginning or end or in between. Like, as long as they don't care about it, right, I can always maintain good relation and healthy atmosphere in the collaboration, right? So uh, that's what I should thank my students and collaborators for that.
Mm-hmm.
Yeah.
So which courses are you going to be teaching in this semester?
So right now I'll be teaching on metamaterials, so mostly about nanophotonics. So I'll be teaching both. I mean, in my course, from whatever I learned in the university, my teachers, as I said, they always stressed on the importance of both theory and experiment. Uh, some students always complain that, like, I make them do a lot in my course, but I hope, like, once they uh, go to start their own research, they'll realize, like I did, my own experience, right? That my teachers made me a lot of numerics and a lot of computational work as part of projects or the exams and all that. Like, so I make them do the whole lot. So I cover a bit of theory, the numerical techniques, and as well as experimental techniques to students.
Mm-hmm.
I mean, are you in the labs with a lot of these students as well? Because you mentioned that these would be
Yes.
undergraduate students, right?
Right.
Yeah. So
So
these,
the
yeah.
yeah, right. So because of this COVID time, so I tried to do it online while teaching the basic optics course, for example. I tried to set up these experiments of diffraction or interference and then show them in the lab, right, by using some cameras and so that's it was appreciated rather than just writing down. I don't use any PowerPoint, so I still do it, work out all the math in the class.
Mm-hmm.
But when I combine the two of showing the lab actual experiments, so people, I mean, the students really appreciate it, and they say that that makes them understand much better.
Mm-hmm.
Wow.
So when you're showing or conducting the lab for your students, are you allowed to have someone in the lab with you like helping you set up, or do you have to do it on your own?
So it depends. If the basic experiments, like I do it myself. So there's sometimes there are already, for example, each student will build his or her own experimental setup. Right. If I have to show their setup, like of course I take their help and say that like, okay, it's built by the student and he's or she is here, and I'll also make them to explain a little bit by themselves.
Hmm.
Okay, so it's a lot of use for there too. I mean, for them too, and your graduate students and like your helpers, let me call it your dirty workers. Where are they from? Are they? You also mentioned that NPL supports a graduate program. So are they now from NPL, or are they from your original lab, or what's the deal with that right now?
So my students in Mumbai are in Mumbai.
Yeah.
And in NPL, I have new students who are uh, Delhi or nearby, like the NPL students are in Delhi.
So the people that are involved with the lab, the dirty workers, are they how much credit do they get for something?
They get all the credit, as I
Oh,
said
they do.
clearly. Like so, they do all the work, right? Like so, I mean, I as a PI, it's my responsibility to make sure that they're trained and they can do things by themselves,
Hmm.
right? And after that, it's their setup, it's their system. They have to own their work,
But
right? It's their thesis at the
on
end.
the paper itself, like your contributors and whatnot,
Right,
your contributors would be listed. Where would
right.
they like? Would they actually provide any input towards the paper? And if so, then maybe they would get on there. But or would they just like be actually like fitting up the work, setting up the experiment before you come in, or like did they actually
Right.
input things as well? Like what were they like?
Right. So the universities have some minimum requirements. So in TAFR, for example, the student to graduate, so they need one publication, one in an international peer-reviewed
Oh
journal,
wow.
right?
That sounds very
So
useful.
right. So the work which they do, the first paper, uh, I discuss the problem with them, with the student, and make sure that they're trained to do that, right? And write the paper, right? And I discuss with them. It's their results. They give me the results. We cross check and we do it the whole thing together. But I write the first draft and then help them. But the second paper onwards, they have to write their own draft and give it to me. Then I will make the changes, corrections, whatever suggestions, and then it's mutually we work on.
Mm.
The students have to write their own papers at the end,
Mm.
right? So
Oh,
from completely from second paper onwards, there is no way I'm going to spoon feed them, right?
that's interesting because writing these papers, currently even in my third year of physics, it's we were told that in a lot of future and advanced physics labs, you like because we were asking each other, okay, why can't we collaborate? Because usually this course that I'm currently in is collaborative based, and this year it wasn't. And the professor had a very interesting idea, and I want to ask if that's the reason why you think they have to write the paper themselves. Because I'm assuming when you collaborate with a lot of other scientists and whatnot, you are writing the paper together, right? But in this case, you're writing the whole paper by yourself, right? So
Right.
that change, like having to write the whole thing by yourself, I'm assuming you think that definitely provides a better understanding for whatever work you're doing, right?
Absolutely.
So then later on, when they've already written it, they've given it to you, you're like, okay, let's collaborate. Then the actual publication that goes out, is that is that collaborated? That is, right? Or is it just his?
Right. Right. In some works, I do the theory or modeling
Okay.
for my collaborators. So they
Okay.
give me the experimental data and then they ask me if I can do some modeling for them. So I do that. For some, I don't understand. I do not, uh, I'm not trained to explain some data, right? So then I collaborate with theoreticians who will do the modeling or theory for me. Right. So once we write the draft and then to better understand, better express things, right? So collaborate different things. Sometimes I just design the structure. Sometimes I only make the samples. So nanofabrication is done in my lab, right? So yes, I mean it depends on which part we do, right? So sometimes we write the draft, we send it out to potential collaborator, and then say that like, look, this is what we think. Could you help us in building a model or correcting us?
Mm-hmm.
That's very useful.
Yeah.
Thank you.
So we've spoken up to now a lot about just a single field, but are there any other fields that you are interested in or have been interested in while studying physics?
Yes, I mean, yes and no. Anything related to optics, yes. I mean, if there is any field where, like I'm not a superconducting expert, but then to detect single photons, I don't mind
Mm-hmm.
learning superconductivity. Right. So it's a continuous process, right? Like so, it's not that like uh, it's near impossible to just do one thing all our entire career, right? So we do keep learning new things and improve. I mean, to improve whatever we know, I think it's required to learn other areas as well.
Yeah,
Right.
for sure.
And have you ever been like a fan of pure math, or do you just see it as a tool to help you pursue your interest in physics?
So as I said, like so in my masters, there is considerable stress put on the theoretical part, right? And when I joined for my PhD in TAF, it's my thesis supervisor. He's a theoretician turned experimentalist. So he also stressed that we have to do both. To be a good experimentalist, you need to be a theoretician as well, right? At least it's a small, big, doesn't matter, but you need to do.
Mm-hmm.
So I've been always told this. So when I worked in Japan, so I could design the device and develop the device parameters, for example, like so how work out the math for these device parameters for that particular device, right?
Mm-hmm.
And then characterize and show the device functionality. So it helps in giving the complete package, but one can never be fully sufficient, and we need to learn from our
All
collaborators.
right. So are you now passing down this wisdom to your students to be both rigorous in
They
the
all
theory and the experimental side?
they all have to.
Mm-hmm.
They,
I actually really like the pressure put onto the collaborate. No, okay, not pressure is the wrong word, but the forgetting the word, but like
emphasis.
the importance
Yeah.
of collaboration,
Yeah.
right? So, can you tell us a little more about it? Because I think a lot of people throughout their high school experience, university experience, when they look at science, they think of, oh, I'm gonna figure everything out by myself because that's what I have to do, and then most people end up hating it. So I guess I mean, what I'm asking is, what, how does that affect, you know, like how these students, okay, I don't think I said that very well. I don't think I said that very well. Um, okay, I forgot what I was gonna say. I just completely mind blanked.
No,
Collaboration.
I
Collaboration.
guess
There it is. Thank you so much.
yeah.
I guess the question was, where does the collaborative aspects help your graduating students? Like, do you see a lot of these students maybe not struggle, but have a little difficulty with a lot of the courses, but then you put them together and all of a sudden they're actually more interested in the course itself? So the question would be, where do you see collaboration taking it, like taking science away from like your own individuality? Like, where does that come in?
Right. Okay. Interesting question. So it's what I try to do is for example, if I give you a problem and say that like you need to solve and then this is your assignment, okay, right? There's so much you can do. Okay? But if I say that like so I make it so that like not just a simple question and then I say that like this is the question, right? And you need to solve this. You need to show me by plotting and doing all the numerical work and plot it and show it to me, it'll take a lot more time, right? So I don't give it to one student. I say that like, okay, three of you can form a group, right? So it becomes like a group work, right? And I insist that in these times, like say, ethics and scientific ethics and all these things is very important, right? So to put that in practice, so I make sure that they specify exactly like what contribution each of them uh, is in that solution which they are giving to me.
Mm-hmm.
Okay? And I ask them openly, like if there is any weightage they want to be given. Somebody did more work, somebody did lesser work. Okay, it's possible, but if they want to give some weightage, so I ask them directly and then they take. So this is kind of like for students in the class, like, so this will help in two ways. One is to make them interact with others, to learn. I mean, the learning can be a lot more faster, and it need not be done. Every bit need not be done by each one of them. Right? It tells that like, so by collaborating, we can learn a lot more, do a lot more.
Mm-hmm. Mm-hmm. And your collaborators, are they? Do you work with them like physically? Do you? I mean, I guess COVID times. Just forget COVID. I mean, before COVID, every question is pre-COVID. So pre-COVID, when you were collaborating with other scientists and whatnot, were they from all over the world? Were they from all over India, or were you physically working with them on the project?
Both ways. So the international collaborators, we send share the data over email, and then we discuss over one of these chats, and then try to do it. And there are also Indian collaborators. They come and visit me, or I go visit them. Right? We spend a couple of weeks depending on the problem. Like, okay, so both in formulating the problem as well as solving, I mean, building some model or something like that. Like, yes, I mean, both are possible. Physical physical proximity is not a necessity for the collaborations.
Okay, that's useful. So when it's not a necessity and when you are not physically in contact, how does the is the process even like how different is it? Because I would think working with someone, I can be like, oh, now it's this, now it's this. I can tell them what's happening at every point of the experiment. We can literally quote unquote collaborate
Right.
on the experiment.
Right.
But in the situation where that's not the case, when the physical distance is a factor, how does that work? Is it like, oh, I have to do this now, I have to wait 12 hours for this guy to respond? Like is it things like that? Like, what are the common problems that you would see sometimes in these collaborative projects?
See, with the student, the first thing happens that we discuss, we exchange the data, like when we are physically together.
Mm-hmm.
Right. So the data analysis and all these things are continuous interactions which happens, discussions and all that. But with the collaborators, it's only when we need, right? Like, so we do not understand our data. We need some specific thing, like, so whether what we're doing is right or wrong. So then we set up a meeting with them, and then first explain, show the data, everything. Okay. Then send a draft and the data to them, and then they will come back at their convenience, because they also are doing their own work, and they have to find time. So something. But there's some collaborators who are extremely prompt, right? So for example, I send a question to one of my senior professors and collaborators, like, so is in US time. So before going to bed, if I send the question, so next day morning when I wake up, the answer is already there. Right? Keeping up pace with such people is challenge,
Yeah,
right?
for
So
sure.
they shouldn't lose interest or think that like I'm not interested, or I'm slow.
Exactly. Because
Right.
with five, six publications a year, that's what I still can't understand. I'm like, how is that even possible? Like, that's a lot of publications, that's a lot of different papers that you're writing. So I'm just like, how are Like, how do you even find the time? I mean, clearly it's just all the combined effort with your collaborators and whatnot that even makes this possible. And
Right.
another question I could have is, what do the collaborators collaborate on multiple projects with you? Like, do you have a bunch of collaborators that you're really close with that you're like, okay, if I have any future project in this field, I know I'm going to ask them? Or is it like new every time?
Uh, I mean, so for example, there's some collaborations which are going on for I don't know, almost 15 years.
Wow.
Wow.
Right.
That's a long time.
Right.
15 years.
So it's just a frequency match, right? Like, so
Wow.
there are always, like, I mean, yes, there are people whom we would like to. Right? There are some people who do most of the work, and uh, you don't really feel at home,
Right.
right? So that won't move on forever, right? So it's one problem and switch off kind of thing, right? There's some uh, who your frequency matches with them, then it goes on, right?
That's important, right? Maybe a final question about photonics, because I was wondering about the process from going to electronics to photonics. Now, again, it might be super elementary, but like go back to when we originally thought of photonics, right? I'm assuming electronics is already there, right? Electronics is
Right.
already a thing. So our question is, how do we make electronics better? Was the photon our first choice into asking that
Right.
question?
Yeah, I guess so, because early times, how was the communication? It was just by lighting fires, right, at different stations, right? So light is always there.
So light is always there. So I guess photon was one of the first ones.
Right.
So I mean, working in this field, where do you think, or what do you think the next step is? I mean, we've already kind of discussed what you think the goal for the field is, but in terms of electronics, photonics, I guess one question could be, do you think that like photonics itself will evolve? Like something new will come up, electronics, photonics, something else? Or or do you think that photonics itself will, just become much more powerful and just supersede electronics?
So uh, what I'm thinking, my own view is that, like, so near future will be a combination of electronics and photonics, right? Integrating the ideas from electronics and photonics into designing a new device, right? So it'll never be a pure photonics thing, in the sense that how do you trigger, how do you modulate, right? You always need some external electric field or magnetic field, or one more optical beam, right? So there's always a combination which will be there. It's not just completely all optical, everything photon, but there will be a combination, because you can do a lot more if you can combine or applied external bias, like electric field or magnetic field is combined.
Okay. At least we have a future. We have a future to see. Very exciting future.
Awesome. So yeah, we've talked about a lot of interesting topics today. It was awesome to have you on.
Do you want to maybe talk about anything else? Anything in particular? Want to just lay it on our audience? Something about what you do or anything like that?
So I'm learning metrology now, what metrology is all about, right? It's a completely different ball game.
Wait, sorry. What is
Uh,
metrology? Sorry, I'm sorry. What is it?
Metrology is the science of measurement, science and art of measurement,
Okay. Okay.
right? So each country has one national metrology institute, right? So NIST in US, or NPL UK, or NPL India. So these are officially the country has decided them to be the metrology institutes.
Okay.
Right? So if you want, like for example, we know about this kilogram, right? Like the prototype of a kilogram or a length bar, right? So these are all kept in these institutes. But in 2019, the countries, I mean, everybody accepted that we should have new definitions which are not based on prototypes, but we should have the fundament, I mean, all the primary standards, for example, kg or meter or right. So these are all defined in terms of the fundamental constants, right? The Planck's constant and the Boltzmann constant and Avogadro number, right? So I mean, so people are right now, they're developing these new standards, where primary standards to measure these different quantities. Right? So here, in a lab, we measure, we remeasure, right? Typically in my lab, like, so we do at least 3 different times we repeat the same measurement, and we repeat on multiple devices, and then we get the statistics and make sure that, like, so what we're reporting is correct. Right? But still there are errors, right? And we don't necessarily give all the error bars and everything in every publication, or it's not needed, right? But here everything is in metrology, every small uncertainty budget. We are using a voltmeter, you're using a current source, right? So how much is the uncertainty in when you're saying that you're measuring 1 millivolt, or when you're saying you're passing 1 ampere current, right? So there is always, everything has to be taken into consideration, and every single measurement has to be reproducible. Right? So it's pretty challenging, and possibly to set up, like, so there's something called CMCs, like, so the calibration and measurement capability, right? So when we say, like, India has the CMC for say 10 volt with say 60 nanovolt uncertainty, right? That's what is the CMC which we have. Right? So to set this, to get this CMC set up in the country and say that, like, India has this CMC, right? So it requires first set up the experiment, then set up the analysis method. Then there will be, the world is divided into different zones. So the India comes under this Asia Pacific Metrology Program, right? So the APMP reviewers will come and check these things. They say, okay, then it again goes to CIPM or the international, I mean, world level reviewers come and then check out again, right? So after all this, like, so there will be some intercomparison. The same sample is sent to multiple countries, and each of them measure and say, okay, this is what I'm measuring. And finally they disclose, okay, this is the original value. Okay. So then they plot the entire thing, is called the intercomparison plot, right? Then we know, right, okay, so India has 2.8 nanosecond uncertainty in the time which we have, like, so right. So what we send to BIPM, like, so that's one of the best in the world. So these things are, it takes 2 to 5 years.
Wow.
Right? But because it just, like, one single institute is doing all this metrology work, right? So the credit they get is a lot less compared to what a scientist in any lab. I mean, as I say, like, so I can publish 7 papers in a year, but I can't set up one CMC in 1 year, right? It takes 2 to 5 years. Right? So it's a lot more challenging and completely different ball game, and the kind of precisions, kind of hard work goes into setting up these CMCs and facilities is really mind-boggling.
That actually reminds me of, like, before the quantum revolution, where scientists and physicists believed that everything was already discovered theoretically. The only thing that could be advanced is in metrology, and just being able to measure things more precisely. And then, of course, we hit that barrier where it's like, wait, that's not all there is. But it's very cool to see that, it's still even though we've discovered that, there are some things beyond the classical world, it's still very important to, be able to perform measurements and be more precise and accurate in the measurements that we do.
Right.
Yeah, no, it's
True.
definitely very useful having this whole idea of measuring more and more precise objects, or not objects, but measuring the same thing with more and more
Quantity,
precision.
yes.
Exactly.
Yeah.
What is there a limit? There definitely is, like an atom's width, or I guess a quark's width. But is there a limit to the amount of precision we can get to? Like if we're trying to more accurately describe something, just like in electronics, when you want to put more and more transistors, there's a limit where quantum tunneling now occurs. So is there a limit? I'm assuming it will just be like the width of a atom or of a quark or something like that. I could be wrong. You can correct me. But is there a limit to precision?
Right. I mean, people keep pushing the limits, right? Like, so if you want to talk about length, right? So what's uncertainty you can go to? So eventually it has to be an atom or,
Right.
right? So right now people go up to picometer precision, right? How do you push, right? If you are talking about optical coatings or something, right? You need flatness. You need to check the flatness. You need to check the roughness of these surfaces, right? So you need to go down to picometer thing. Right? That's only the requirement. Right? But then if we have newer requirement which says that, like, no, we need better than picometer. Yes, of course we need to push it below and find ways. So it's always depending on the need and necessity, I guess.
I don't even think people understand the the small. No, that's not the word. Like how small?
Scale.
Yeah, the scale of a picometer and a femtometer and like they're so, like, you can't even imagine these scales. Picometer being 10 to the minus 12 meters is just I don't even, like, you can't even think of that, and we're dealing with these at that scales is just awesome. It's just awesome.
Awesome.
Yeah.
Well, I guess those were all the questions that we had for you today. We want to thank you for coming on to the podcast. We had a very good time today.
Yeah, definitely. I mean, thank you so
Thank
much
you very much. Yeah.
for this whole thing here today, and taking the time out of your day. I know it's quite late now. It might be getting to come and sit with us today. So I just want to thank you, taking it out of your Sunday night.
No, it's Sunday night.
Sorry, I'm bad. But
I guess like it's more challenging for you because it's the getting up and
Yeah.
doing on Sunday morning.
It was no issue.
no issue at all. We're good with waking up.
So yeah, to everybody that's listening to the podcast right now, make sure to follow us wherever you're listening. Come on YouTube and check out the video, and also subscribe and leave a comment. And that's
basically all you need to do.
So yeah, thank you so much for listening. This was episode number 95. And yeah, I'm your host, Parker.
And I'm Ray, and we shall see you soon.
Bye, guys.